So the next exercise we can look at is actually the most important ratio which we recall from our theory, which was not the power itself as an absolute value, but the power to noise ratio. So one thing you can do is you can reduce your antenna gain and you can reduce your total power to the lowest values possible. And in this case, we can see that, of course, if we have no noise, well, we might still be able to receive or transmit. So I'm showing some values here for all the fields, which you can, of course, copy. And you can check that with this configuration, you can still receive packets since there is no external noise. Of course, when I tick the interference or jamming, what we are going to get is some noise. And as I told you previously, it doesn't just add one frequency of sine noise, it also adds the total floor of the noise. It increases it. So we also get an effective white noise with a higher level. So one thing we can see is that even though we might have very little absolute power, so you can see the values I have set up here, and if I have no noise, if I have no interference or jamming, now you can see that I am still receiving properly. But what happens is that if I turn on the jamming, this increases my noise floor by about 20 decibels. And even if the frequency which is used, so I'm gonna, for example, in this case, I'm transmitting at 450 megahertz and receiving at 450 megahertz, and the jamming is at around 430 megahertz. So even though it is far away enough, this central peak frequency of the jammer, since the total noise floor was raised by about 20 decibels, I already have trouble in receiving because let's say the white noise level, so the effective temperature, if you like, of the system has increased. So I already have trouble receiving, and I get a much higher packet error rate. And in fact, if I'm at this lowest configuration of the gains and the power, I do not even get any useful information. Now, of course, we can correct this either by reducing the noise, so by removing this noise level, or by increasing our own transmitter power. So if we start increasing slowly either the power of the transmitter, so if I put it to 31 dBm, much higher power, you can see that already I have no trouble in receiving the packets, and my packet error rate is significantly dropped. So you recall that for each modulation scheme, we had a correspondence between the bit error rate and the EB over N naught, so the energy per bit per unit spectral density of the noise. Now, getting to the packet error rate is a bit harder, because this packet error rate, it depends on the structure of the packet. So maybe we have 1 in 10 wrong bits, so maybe we have 10% of the bit error rate, but if our packet is composed of 10 bits, then this will be a whole wrong packet. And so the translation from one to the other is not so obvious. And what you should just keep in mind that the two are somehow related. So if you know the exact structure of the packet, you can define the packet error rate as some function of the bit error rate. So the two are related. And again, this measurement which we make here, this PER, which we have as an output of our simulation, it gives us some sense of also of the BER, the bit error rate. Now, of course, if we change the different modulations schemes in our case, they're all the same in terms of being JFSK. The only thing we change is the frequency deviation or the rate. But we can see by playing around with the other parameters, full link budget. So just to give you a very simple example, we can do the same link budget for UHF, S-band, and X-band in terms of all of the other parameters being fixed, and we can see how essentially the difference of each of them is pronounced. So for example, in UHF, we can have, let's say, an omnidirectional antenna. So I'm going to put the antenna gain to being 0, and we can have, let's take an ideal case, let's say very few feeder losses also, let's put it to 0 dB. And let's keep our packet size and count and the delay constant. And I'm going to center on 437. I'm going to keep the same modulation scheme. I'm going to put a distance which is the LEO satellite, so let's say 400 kilometers. This is a typical distance for a LEO satellite. And after computing the free space path losses, again, putting, let's say, 3 decibel antenna pointing loss, which is something realistic, so twice reduction, 3 decibel polarization loss, and maybe the maximum here, 1 decibel of atmospheric loss, I can start the transmission and I can see my packet error rate with no external interference, with no external jamming. Now, of course, I can do the same thing by activating the external interference, and after starting the same transmission, what I can see as a final packet error rate is going to be something a bit higher. Now, in this case, I am safely within the bounds, let's say, of the secure signal, so I can still understand my signal, I can still receive the packets with no problems, but the error rate is going to be a bit higher. One of them has a chance to be wrong. And in the past, we related this to the bit error rate. Now, of course, we're doing it to the packet error rate, but we can try something very similar in the S-band and the X-band, and we can see the specifics of each of them. So what you are supposed to do here now is a link budget, essentially. So this RF tool is going to give you the means to check if your link budget works properly, but we are essentially doing the same thing which we did theoretically before. So we are evaluating for different parameters of the receiver and transmitting chain, and for different distances and additional noises and loss sources, we are evaluating what's going to happen and testing it out physically if this is what happens. So you can notice on the S-band that, let's say we fixed to 2.1 gigahertz. Of course, we need to fix the receiver to 2.1 gigahertz as well. Let's use the second 2400 baud rate with 600 hertz of frequency deviation for the RF mode. And let's keep our antenna power to the maximum. Here, of course, we can get a much higher antenna gain. For S-band, in general, making the patch antennas we have already seen, you can get a much better antenna gain than for, let's say, for what we saw for the UHF. We used omnidirectional because it's roughly more realistic. It's low enough frequency that it doesn't need that much directivity. So for the S-band, we can put the highest possible gain here, so 10 dB. And keeping, again, ideal feeder and all of these additional payloads fixed, we can again see that for the same distance, same parameters, we're going to have a transmission which can now support even higher transmission rate, but we'll see this later, and which, of course, can be affected a lot more by the atmosphere. So, for example, we can have as much as 3 dBs here coming from the atmospheric losses, and after computing our free space losses, we're going to see that their contribution is going to be much higher. So, in a sense, you see again that we have a sort of need to increase the antenna gain when we go to higher frequency, simply because all of the frequencies which we're using are going to be dampened more by the atmosphere. We're going to have more losses. Also, the chance of harmful interference, because they're more used, is going to be higher. And we can see that if we increase our total noise, so again, if we turn on the interference or jamming, we're going to get sort of raising the total noise floor, even if we keep it at, let's say, a very different frequency, but we're still going to have a very large difference. So if we go to X-band, all of these effects which we just said, they're going to be even more pronounced, because on X-band, our antenna is going to be more sensitive to the pointing, a bit more directive, and of course here also the feeder, it may play a much larger role, but on the other hand, we can support a much higher transmission rate with roughly the same configuration. So you can play around here as well. You can run a few different simulations, changing each of these parameters, and you can see that, for example, if after computing our free space path losses for the same altitude, by introducing noise, we're going to get, of course, here even more sensitive to this external noise PER, so packet error rate. And we can play around, and we can see that for the same noise, in each of these cases, because in all of these cases, this interference, it has a, let's say, a white noise component, which raises the total noise level by about 20 dB, and it also has a monochromatic component, which we're going to see in a while. So we can see how it affects our communication, the white noise component so far, and how all of these parameters, including the modulation type in terms of frequency deviation, makes the whole system more robust or more prone to losses.
So one last thing you can see with the external jamming, so right now I have it on, is also what happens when we approach the source. So when we approach the source frequency in which our system works. So right now I've set up the jammer at 435 megahertz, and we are transmitting and receiving respectively at 437. So what happens when I hit the simulation is that you see there is still no problem. We're far enough from the jammer because we have a bandwidth of about 10 kilohertz. You see our deviation is 4.8 kilohertz, so have a bandwidth of about 10. So this is far enough not to affect us at all. But what's going to happen if we start approaching actually the frequency at which we are transmitting? So let's put it to 436.3, for example. Let's start to get closer and let's start increasing this frequency to see how our packet error rate might change. So you see there is no change right now because it's still far enough. As I said, we have just about 10 kilohertz of bandwidth, and this is still about 770 kilohertz away from us. So let's keep increasing this number. So you see we are already about 100 kilohertz away from our actual carrier frequency, and now you can see the percentage has slightly increased, because if you noticed in the beginning we had absolute zero all the time and it was very, very low, but still it's not very significant. It's just 1%, so it's still not something significant. But let's start going really close. So we said we have about 10 kilohertz of bandwidth, and when we have this 0.1 megahertz, this is 100 kilohertz, so we're still 100 kilohertz away. So let's start increasing the second decimal number. So let's get really close. Let's go just 20 kilohertz away from our carrier. So right now we're jamming at 436.98, and let's play. And so we're still far enough. We're still securely far away enough that there is really no problem. So I'm going to put it to 436.99, and I'm going to hit run. And okay, so you see this is close enough now. It's already within our bandwidth and we're getting nothing. But what we can do, and we're going to make this the next run, is we can actually actively dynamically change this frequency of the jammer while we're carrying out the transmission. So I'm going to increase the packet count. I'm going to get really close. I'm going to get just 10 kilohertz away from our actual carrier, and we expect now to really have jamming. And you can see indeed that we are not receiving anything. So we're sending, but we're not receiving anything. Now what you can do is you can, while this transmission is carrying out, you can actually untick the jamming, and you can see what happens if you actively move it away. So I'm going to turn it on again, but at a lower frequency, and you see now we are getting the packets, and dynamically I can change this while the receiving is carried out, and I can right now jam exactly at this frequency, and you see as soon as I ticked the jamming, we stopped receiving any more packets, and we have exactly 186. And if I stop it now, we're going to keep receiving more packets. So you can dynamically play with this, and you can see how your variable jammer would influence your transmission. And of course, you can do this with your own external noise generator, as we said previously, connecting it to the free space module, and you can get a much more realistic picture of what this would look like.